In this video, we'll break down the attention mechanism and understand how transformers changed NLP completely. We'll start from the problem with RNNs, move into sec-to-sec, see how teacher forcing works, and then understand why attention solved the long context problem. Along the way, you'll get quick quizzes to test your understanding. Chaliye, let's begin. Transformers are the foundation behind modern large language models. The key reason they became so powerful is attention. Instead of compressing everything into one memory state, the model can look at relevant parts of the input directly. That is what made long text understanding and generation much better. Before transformers, RNNs and LSTMs were common for sequence tasks, but they process text step by step, and that creates a limitation. For long sentences, important details from earlier words can get diluted. In practice, the final hidden state has to carry too much information. In language translation, words do not always map one-to-one in the same order. For example, an English sentence may become a Hindi sentence with reordered words and even extra grammar words. So the model must understand context, not just copy words position by position. Now let us look at this in a simple table format.
RNN vs sec-to-sec vs transformer.
How sequence models evolved? Here is the big picture. A plain RNN struggles with long-term memory. Sec-to-sec improved sequence handling, but still relied heavily on a context vector. Attention allowed the decoder to access all encoder states. Transformers took that idea fully and made contextual processing much more effective and scalable. Sec-to-sec introduced a very important idea. Use one network to encode the input sequence and another to decode the output sequence. This was useful because the input and output lengths could be different, which is very common in translation and summarization tasks. Now that we've covered RNN to transformer, let's test what we've learned so far.
Here's quiz number 1. See if you can get it right.
Question 1. What is the main weakness of basic RNNs in long sequences? The correct answer is, they forget long-range context. RNNs process step by step, so earlier information can fade as the sequence becomes longer. Question 2. In sec-to-sec, what does the encoder mainly do? The correct answer is, convert input into a context representation. The encoder reads the input sequence and creates a representation that the decoder can use. Question 3. Why was attention a major improvement over plain sec-to-sec? The correct answer is, it allowed direct focus on relevant input states. Attention lets the model look back at relevant encoder states instead of depending only on one compressed vector. To train a sequence model, words must first be converted into numbers. The article uses one-hot encoding for simplicity, though modern systems usually use embeddings. On the output side, special tokens like start and end are added, so the decoder knows when to begin and stop generating. As the encoder reads each token, it produces hidden states. These hidden states capture both the current word and the previous context. In older sec-to-sec style systems, the model tries to summarize the full sentence into a compact context representation, which is then passed to the decoder. During training, the decoder often uses teacher forcing. That means instead of feeding its own wrong prediction into the next step, we give it the correct token from the target sequence. This reduces error accumulation and helps the model learn faster and more stably. At each output step, a softmax layer converts scores into probabilities over the vocabulary. The correct word should get the highest probability. To train the model, categorical cross-entropy is used as the loss, and then backpropagation updates the weights across many epochs. Now that we've covered sec-to-sec basics, let's test what we've learned so far.
Here's quiz number 2. See if you can get it right.
Question 1. Why are start and end tokens used in the output sequence? The correct answer is, to mark decoding boundaries. The decoder uses these special tokens to know when generation starts and when it should stop. Question 2. What is teacher forcing? The correct answer is using the correct previous token during training. Teacher forcing supplies the actual target token to the next decoder step during training. Question 3. Which loss function is commonly used for word prediction over a fixed vocabulary? The correct answer is categorical cross-entropy. Predicting one word from many vocabulary options is a multi-class classification problem, so categorical cross-entropy fits well. Attention solved the biggest pain point of older sequence models. Instead of forcing the whole sentence into one vector, the decoder can compute relevant scores and focus on the most useful encoder states. This means details from earlier words remain accessible when needed. In attention, each output step does not look at the input equally. It assigns higher weight to the most relevant input words. So while generating one translated word, the model may strongly attend to one source token and lightly attend to others. This creates much better alignment. Transformers generalize the attention idea beautifully. They use self-attention to let tokens interact with each other directly, along with feed-forward layers, normalization, and skip connections. Depending on the design, we get encoder-only models like BERT, decoder-only models like GPT, or full encoder-decoder systems like T5. Now that we've covered attention core idea, let's test what we've learned so far.
Here's quiz number 3. See if you can get it right.
Question 1. What problem does attention mainly solve in older seq-to-seq models? The correct answer is single context bottleneck. Attention reduces dependence on one compressed vector by letting the model access all relevant states. Question 2. In attention, what do the weights represent? The correct answer is importance of input positions. Attention weights show how much focus the model gives to each input position for a specific output step. Question 3. Which statement best describes a transformer? The correct answer is a model built around attention mechanisms. Transformers rely on attention as the central mechanism for contextual processing across tokens. If you understood this flow from RNN to sec to attention to transformers, you've already built a very strong foundation for learning modern LLMs. In the next step, you can go deeper into self-attention, scale-product attention, causal masking, and multi-head attention. Keep learning, keep building, and milte hain in the next one.